All right, we're back. We're going to be on page 6 of notes 13 of Calc C, and we're talking about Euler's method, which is a method of approximating the solutions to a differential equation. It's like tangent line approximations gone mad. You just use a lot of tangent lines, but because it's the same thing every time, we generalize it, and we're able to do it in a table form instead of like you kind of like skip out on the calculus, honestly, when you do this. I mean, you need to know the derivative, but like the premise is that you have the derivative. I think that without understanding anything, we could give this to like an Algebra 2 student and they would probably be able to do it. So don't be intimidated, it's just process. All right, so let's see, what are we doing? We're gonna use Euler's method, step size of 0.1 to approximate y of 0.5. Oh, so many steps. And we're gonna compute the exact values. Whew. Also, I think there's like, well, whatever. I think there's gonna be a huge problem with this at some point, but we'll find out. So, all right, so 0, when x is 0, y is 3, that's given. And therefore, that's the actual value. We're not going to be able to find the actual value for like a second or two, like minutes. But dy is going to be f prime of xy delta x. Okay, so our step size is 0.1, 0.1. And then what are we supposed to do? We're supposed to do y squared minus 1. So that would be 9 minus 1 is 8. So that's 0.8, and that's not bad. So we can add that and get 3.8, and that's the end. That's where I'm going to stop doing these by hand. So I'm going to switch over to the calculator, but I'm going to fill in the table as I go. So I'm going to be filling in the notes. I'm not switching back and forth every time, but follow along. Let's see. So I'm not even going to use the built-in thing. I'm going to do it. So I'm going to define f prime of xy is going to be equal to y squared minus 1. All right, I think that's probably good. And then, so the first thing I want to do is, well, let's 3 plus 0.8. I got to get in the mood, you know, like, all right, so there we go, 3.8. Now I need to do 0.1 times y squared, so that's 3.8 squared, and then plus, nope, minus 1. Oh, did I forget to subtract 1? No, I did not. Okay. So 1.3. So I'm writing that down. So that's I'm writing down 0.1, 3.8 squared minus 1. And then I'm going to just say that that equals 1.344. And then I need to do 3.8 plus this value that we just found to get 5.144. 5.144. I will check this on the I will use Euler's the table method to check it, but for now I need 0.1 times the previous answer squared minus 1, and I get 2.546. So 0.1 5.144 dang it, squared minus 1 is, that's got, okay, I'm gonna do 2.546. I need to add these together to get a new y value. It's so annoying to do it multiple times. 7.690. So then I do 0.1, 7.690 squared minus 1. So that's just for writing purposes. Can I do this? I wish, no. I was hoping this would just say answer. Delete this and say answer. Okay, so 5.814, let's say. And then we gotta add these. It's so much work. And then it's like, it's not even like the half of it. 13.504. Imagine if this is all wrong. Oh, the tragedy. I should have done the Euler table first so that I like knew the answer, but I didn't, so, you know, deal with it. All right, we're deleting a bajillion things to answer 18.1, 13.504. This is the last one though. 18.135. So I gotta add this to this. 31.639 is my claim. I think that's wrong by a bajillion, but I'm not actually sure. So now I'm going to check Euler. All right. Y squared minus 1 xy. X starts at 0 and is going to end at 0.5. Y starts at 3 and we're going by 0.1. Okay, so these are the right values according to Euler's method. Fine. And now the problem actually, the next part of the problem actually tells you f of x. So f of x is 2 plus e to the 2x over 2 minus e, y, e to the 2x. Boom. F of 0.1, f of 0.2, f of 0.3, f of 0.4, f of 0.5. Let me fill these in. So if you're filling them in with me, you will have noticed something bizarre and tragic has occurred. 21. It's like pretty good until you get to 0.3, or well, 0.4 really. And then suddenly negative. Like, what's going on? Well, we didn't think very hard about this problem. And what might have happened, I think we jumped over an asymptote. And then the tangent lines just keep going because they don't know what to do, right? Because you're always using a fake point to write your new tangent line. The tangent lines jumped straight over the asymptote, and then they're totally inaccurate. So if I were to graph the function, graph f of x, you can see there's an asymptote here, and we jumped over it. And when we jumped over it, we're still up here because the fake tangent line point is still up here, and it's going to keep getting worse. What should have happened is we should not have used an initial condition over here to approximate something over here. That's where we went wrong. Like, the problem was wrong to begin with. Let me see if I get denominator of f of x, and I solve this. So, ew, what am I even doing? There we go. 0.347 vertical asymptote. We jumped over it. That's why the answer between 0.3 and 0.4 went nuts. So you do have to watch out for that. So, I mean, I think that's like a pretty good, that's the Euler's part. So I'm gonna go back to the notes so you can just see what I wrote. I'm gonna cut it there and come back because we're gonna solve the differential equation and we're gonna verify the answer. So we're gonna do like two different things, both of which might take a little bit. So this is the table that we ended up with. And like here is where things have gone kind of haywire, right? It was good before that, it's good here, but then terrible on the next one. And what happened was vertical asymptote, we jumped it. Jumped a vertical asymptote. And once you've done that, things are nuts. Like, anything could happen. Like, there's no way to know. So, all right, I'm gonna stop this video here. I'll be back in the next one, and we will keep going. So I'll see you there.